Let's get ready to explore. Number 10. The singularity inside black holes. In 1915, Albert Einstein published his general theory of relativity, a set of equations so precise they could predict the orbit of Mercury to extraordinary accuracy. Within months, physicist Karl Schwarzschild had found something buried inside those equations that Einstein himself refused to believe. Schwarzschild derived his solution while serving on the Russian front during the First World War, and what he found was not a curiosity. It was a warning. At the center of every black hole sits a singularity, a point where density becomes mathematically infinite, where space-time curvature becomes infinite, and where the equations that govern all of physical reality produce something they should never produce, a division by zero. These are not approximations or rounding errors. They are the universe's equivalent of a system crash, a place where the software of physics reaches a command it cannot execute and simply stops. In 1965, mathematician Roger Penrose proved rigorously that singularities are not mathematical accidents. They must exist. His singularity theorems, which would eventually earn him the Nobel Prize in Physics in 2020, demonstrated that once matter collapses beyond a critical threshold, the formation of a singularity is geometrically unavoidable. General relativity does not merely permit these regions of broken physics. It demands them. Stephen Hawking's work in 1974 deepened the problem. He showed that black holes slowly radiate energy and eventually evaporate, which raised a devastating question. What happens to the information encoded in all the matter that fell in? Quantum mechanics insists information cannot be destroyed. General relativity, near the singularity, appears to destroy it without hesitation. Every equation physicists use to describe reality produces nonsense at a singularity. These are the same equations that guide our satellites, power our nuclear reactors, and predict the positions of planets centuries in advance. They work everywhere in the known universe, except here, at a point that Penrose proved must exist. What does it mean to call something a law of physics if it only applies sometimes? Number 9. The Planck scale, where space itself dissolves. In 1899, physicist Max Planck was trying to solve a deceptively simple problem: how to accurately describe the energy of heated, glowing objects. In working through the mathematics, he stumbled onto a set of natural units that combine the speed of light, the gravitational constant, and his own newly discovered quantum of action into a single measurement. The number he arrived at was so small it seemed meaningless. It was not. The Planck length, measuring 1.616 times 10 to the power of negative 35 meters, is approximately 100 billion times smaller than a proton. At this scale, the familiar geometry of space simply ceases to apply. Physicist John Wheeler proposed in 1955 that at this resolution, space-time itself becomes what he called quantum foam, a seething, chaotic froth where the smooth fabric of space breaks into violent, probabilistic fluctuations that have no definite geometry at all. This is not a frontier we have failed to reach yet with sufficiently powerful instruments. It is a fundamental wall. The Planck time, just 5.39 times 10 to the power of negative 44 seconds, represents the shortest interval of time that carries any physical meaning. Below it, the very concept of before and after dissolves. The two greatest frameworks in all of physics, general relativity and quantum mechanics, produce irreconcilable and catastrophic contradictions at this scale. Contradictions that no refinement of either theory has yet resolved. Loop quantum gravity and string theory both attempt to bridge this gap, describing what space might look like at and below the Planck scale. Neither has been experimentally confirmed. The energy required to probe this scale directly, the Planck energy, is so extreme that a particle accelerator capable of reaching it would need to be the size of a galaxy. The universe appears to have a minimum resolution, a pixel size below which reality becomes undefined. We do not live at the bottom of the cosmos. We live somewhere in the middle, with an entire layer of existence permanently hidden beneath our feet, unreachable not by lack of technology, but by the geometry of physics itself. Number 8. The Big Bang singularity, before time began. In 1927, Belgian physicist and Catholic priest Georges Lemaitre proposed something that sounded almost theological. The universe had a beginning. 2 years later, Edwin Hubble confirmed it observationally at the Mount Wilson Observatory in California, showing that galaxies were racing away from each other in every direction. When physicists ran the mathematics of that expansion backward, rewinding the cosmic clock toward its starting point, they arrived somewhere that should be impossible to describe at all. At the moment designated as t equals 0, the equations produce another singularity: infinite temperature, infinite density, infinite space-time curvature. But this singularity is profoundly different from those inside black holes. It is not a location in space. It is the origin of space. It is not a moment in time. It is the origin of time. Every physical law we know, every constant, every force, every rule governing matter and energy emerged from this event. They did not govern it. In 1970, Stephen Hawking and Roger Penrose published their singularity theorems, extending their earlier work to prove that the Big Bang singularity was not a choice or an assumption. Under general relativity, it was mathematically unavoidable. The universe did not slowly emerge from some pre-existing state. It began, formally and provably, at a point where the equations of physics issue no predictions whatsoever. The James Webb Space Telescope, launched in December 2021, can observe the universe as it existed within the first few 100 million years after the Big Bang, closer to the beginning than any instrument in history. Yet the Planck epoch, the first fraction of a second after t equals 0, remains permanently beyond observational reach. No light, no signal, no information can carry data from that era to us. The laws that would govern such signals did not yet exist. Every physical law we have ever discovered, tested, and relied upon was born at a single instant 13.8 billion years ago. But what was present at that instant to do the birthing? And what were the rules before the rules existed? The question is not merely unanswered. Under current physics, it is unanswerable, and perhaps permanently so. Number 7. Neutron star interiors, matter beyond known states. On July 4th, 1054 AD, Chinese imperial astronomers recorded a new star blazing in the constellation Taurus, so bright it remained visible in daylight for 23 consecutive days. Nearly 1,000 years later, in 1968, astronomers identified what that stellar explosion had left behind: a neutron star at the heart of the Crab Nebula, spinning 30 times per second and pulsing with the regularity of an atomic clock. It was one of the most extreme objects ever confirmed to exist. And what lies inside it, no one fully understands. Neutron stars pack between 1.4 and 2.0 times the mass of our Sun into a sphere roughly 20 kilometers across, approximately the width of a city. Their core density reaches approximately 10 to the power of 14 grams per cubic centimeter. A single teaspoon of neutron star material would weigh, very roughly, 1 billion tons on Earth. At these pressures, the atoms that make up all familiar matter are completely crushed out of existence. Electrons are forced into protons, creating a dense fluid of neutrons unlike anything in ordinary physics. But that is only the outer core. Deeper still, conditions may become so extreme that neutrons themselves dissolve, their constituent quarks freed into a state of matter called a quark-gluon plasma, a phase of matter that last existed in the universe fractions of a second after the Big Bang. Some theorists propose even stranger possibilities. Strange matter, composed of up, down, and strange quarks in equal proportions, a form of matter that has never been observed anywhere and that current physical models cannot fully describe. NASA's Neutron Star Interior Composition Explorer, known as NICER, has been measuring neutron star radii from the International Space Station since 2017, attempting to constrain what the interior might look like. The gravitational wave event GW 170817, detected by LIGO in August 2017 from a neutron star merger 130 million light-years away, provided the first indirect observational clues about interior properties. Both efforts have narrowed the possibilities. Neither has resolved them. Inside a neutron star, sitting just 20 kilometers across and visible within our own galaxy, there may exist a form of matter so alien that every law of physics you have ever encountered becomes not just inaccurate, but completely irrelevant. We have studied these objects for decades with the most sensitive instruments ever built. We still do not know what is inside. Number 6. White holes, where physics runs in reverse. In 1960, mathematicians Martin Kruskal and George Sikaris published the complete mathematical solution to Einstein's field equations for a region of extreme gravity. They were attempting to describe every possible region of spacetime around a gravitational singularity, mapping the full geometry of what we now call a black hole. What the mathematics returned was not one exotic object, but two. On the other side of the equations sat something that behaved exactly like a black hole, except running entirely in reverse. A black hole is defined by the fact that nothing inside it can escape, that matter and light fall inward without the possibility of return. A white hole is the mathematical opposite. Nothing can enter it, and matter and energy erupt outward in a violent, continuous expulsion. Soviet physicist Igor Novikov developed the theoretical implications of these solutions through the 1960s, and the concept became a formal object of study. The mathematics was not ambiguous. The equations that correctly predicted gravitational waves, the expansion of the universe, and the bending of light around stars required white holes to exist as valid solutions. The problem is that another equally fundamental framework in physics, the second law of thermodynamics, states unequivocally that entropy in a closed system cannot spontaneously decrease. A white hole, expelling ordered matter and energy outward, would violate this law directly and catastrophically. So physicists found themselves in a position that has become a recurring theme at the edges of their discipline. Two separate, rigorously tested frameworks giving directly and irreconcilably contradictory answers. In 2014, physicists Carlo Rovelli and Francesca Vidotto proposed a striking resolution within the framework of loop quantum gravity. They suggested that black holes, after slowly evaporating through Hawking radiation over astronomical timescales, do not simply vanish. They transition into white holes, releasing their stored information in a final, explosive burst. Some theorists have gone further, proposing that the Big Bang itself may have been a white hole event, the expulsion of matter from a singularity that existed in another region of space-time entirely. The equations that have never been wrong are demanding that these objects must exist. The equally tested laws of thermodynamics insist they cannot. Both cannot be right simultaneously. Somewhere in the gap between those two answers, one of our most trusted frameworks of physical law is giving us a result it should not be able to give. Number 5. Quantum tunneling, objects that ignore physical barriers. In 1928, physicist George Gamow was confronting a problem that classical physics had declared already solved. Radioactive nuclei decay when particles escape the nucleus, but the calculations showed unambiguously that those particles did not possess enough energy to overcome the electromagnetic barrier holding them inside. By every rule of Newtonian physics, the particles could not get out. Yet they were getting out, measurably, consistently, and predictably. Gamow's answer changed physics permanently. The particles were not going over the barrier. They were going through it, not by breaking it or tunneling around it in any physical sense, but by exploiting the quantum mechanical reality that particles do not have precise, fixed locations. They exist as probability waves, and those waves extend beyond barriers, giving particles a calculable chance of simply appearing on the other side without having traversed the space in between. Gamow's formalization of quantum tunneling provided the first successful explanation for radioactive decay, and the implications immediately proved far larger than anyone had anticipated. The sun is producing energy right now solely because of quantum tunneling. At the temperatures inside the solar core, protons do not actually possess sufficient energy to overcome their mutual electromagnetic repulsion and fuse together. Without tunneling, the probability calculation shows the sun should not be able to generate nuclear fusion at all. It is tunneling through the classical barrier that enables fusion to occur, and by extension, it is tunneling that makes every star in the universe shine. Remove this one violation of classical physical law, and the cosmos goes dark. The scanning tunneling microscope, developed by Gerd Bienig and Heinrich Rohrer at IBM Zurich, exploited this principle so precisely that it earned them the Nobel Prize in Physics in 1986. The device images individual atoms by measuring the current produced by electrons, tunneling across gaps too small to be crossed classically. In more recent experiments, physicists have observed what appears to be the Hartmann effect. Under certain conditions, tunneling time does not increase as barriers grow thicker, suggesting that particles may traverse thicker barriers in no more time than thinner ones, in ways that still provoke fierce theoretical debate. The law that says a physical object cannot pass through a solid barrier is not merely bent at the quantum scale. It is abolished every second inside every star in the universe. The sun is shining because particles are routinely doing something that classical physics declares to be physically impossible, and it has been doing so for 4.5 billion years. Number 4. Naked singularities and the cosmic censorship conjecture. In 1969, Roger Penrose had already proven that singularities, points where physical laws completely break down, must inevitably form inside collapsing stars. Now he faced a second, and in some ways more disturbing question. His singularity theorems said nothing about whether those regions of broken physics had to remain hidden. And if a singularity were ever to become visible to outside observers, the consequences for the laws of physics would be unlike anything science had previously contemplated. Inside a black hole, the event horizon acts as a one-way boundary. Whatever chaos reigns at the singularity, whatever catastrophic breakdown of physical law occurs there, it is sealed away from the rest of the universe. No signal, no particle, no information can escape to communicate that breakdown outward. Penrose called this arrangement cosmic censorship and proposed in 1969 that the universe, somehow, always ensures singularities are clothed behind horizons. He could not prove it, and more than 50 years of effort by some of the finest mathematical physicists alive has not proven it either. A naked singularity, one not enclosed by an event horizon, would be causally connected to the outside universe. The infinite curvature at its core would not be isolated. Its effects would propagate outward like light, reaching every observer within its range and collapsing the predictive power of physical law for everyone it touched. In 1991, physicists Stuart Shapiro and Saul Tucholsky ran numerical simulations that appeared to produce exactly this forbidden configuration under certain initial conditions. Physicist Matthew Choptuik found further evidence in 1993, identifying what appeared to be a critical threshold at which collapsing matter could form a naked singularity rather than a cloaked one. Stephen Hawking took the question seriously enough to make a formal scientific wager. In 1991, he bet Kip Thorne and John Preskill that cosmic censorship held and naked singularities could not form in nature. In 1997, he conceded the bet, acknowledging that the numerical evidence had introduced genuine doubt. Rotating black holes described by the Kerr solution, the most physically realistic black hole model, mathematically produce naked singularities if their spin exceeds a specific critical value. Whether that threshold can be reached in nature remains an open question. Roger Penrose proposed this conjecture not to describe how physics behaves, but to protect it from a scenario he found too disturbing to accept. If he is wrong, there may exist objects in this universe whose very visibility destroys our ability to predict anything at all within their reach. After 55 years, we still cannot prove the universe is following its own rules. Number 3. The firewall paradox, where three laws break simultaneously. In July 2012, 4 physicists at the University of California published a paper that detonated quietly inside the theoretical physics community and has not stopped reverberating since. Ahmed Almheri, Donald Marolf, Joseph Polchinski, and James Sully had set out to examine what a single observer would experience falling into a black hole. What they found, working through the implications with careful rigor, was not an answer. It was a proof that physics is broken, and they could not determine where. Their argument, which became known as the AMPS paradox after their initials, identified a three-way contradiction at the event horizon of any black hole. Quantum mechanics requires that information is never destroyed, which means information falling into a black hole must eventually escape. For this to happen, the particles radiated by the black hole must be quantum entangled with both the interior and the exterior of the horizon simultaneously. But quantum mechanics also forbids a particle from being maximally entangled with two different systems at the same time. The only resolution Almheri and his colleagues showed was that the horizon itself must be a wall of lethal, high-energy radiation, a firewall, incinerating anything that crosses it. This conclusion created an immediate and equally severe problem. General relativity's equivalence principle, one of its most foundational and carefully tested statements, predicts that a freely falling observer crossing an event horizon should feel nothing unusual at the moment of crossing. Space there is not special. The horizon is not a physical surface. The firewall prediction violates this directly and completely. The three frameworks in conflict, quantum mechanics, general relativity, and the equivalence principle, are not speculative theories. They are the most rigorously tested foundations of all modern physics, confirmed by thousands of independent experiments across more than a century. Stephen Hawking entered the debate in 2014, publishing a paper in Nature Physics proposing that event horizons in the classical sense may not exist, replacing them with what he called apparent horizons that fluctuate according to quantum effects. The same year, Juan Maldacena and Leonard Susskind proposed the ER equals EPR conjecture, suggesting that quantum entanglement and wormholes may be the same phenomenon described in different languages, a proposal that, if correct, could dissolve the paradox entirely. Neither proposal has achieved consensus. The debate continues as of 2024, with no resolution in sight. In 2012, 4 physicists proved with paper and mathematics that at least one of the 3 most tested and confirmed laws in all of physics must be false, not incomplete, not approximate, false. More than a decade later, no one has agreed on which one. Number 2, the measurement problem. Reality does not exist until observed. In October 1927, the 5th Solvay Conference convened in Brussels, gathering the greatest concentration of scientific minds in history into a single room. Einstein, Bohr, Heisenberg, Schrödinger, Curie, Planck, and Pauli were among the 29 attendees, and they were arguing about something that none of them could fully accept: the new theory of quantum mechanics, which had already proven spectacularly accurate in every experimental test, appeared to be saying something about the nature of reality that bordered on the philosophically intolerable. The theory's core claim was not that particles have unknown properties that we simply lack the tools to measure. It was far more radical than that. Prior to measurement, particles do not possess definite properties at all. An electron does not have a location. It has a probability distribution across all possible locations simultaneously. It does not have a definite spin. It exists in a superposition of all possible spin states at once. The act of measurement does not reveal a pre-existing value. It creates one. This is not a feature of early, incomplete quantum theory. It is the theory, confirmed with extraordinary precision in every experiment performed in the century since. The double-slit experiment makes this explicit in a way that no amount of classical reasoning can dissolve. Fire a single photon at a barrier with two narrow slits, and it produces an interference pattern on a detector behind the barrier, as though it passed through both slits simultaneously. Place a detector at either slit to observe which one the photon uses, and the interference pattern vanishes instantly. The photon now behaves as a particle that passed through exactly one slit. The act of observation does not merely disturb the system, it changes what physically happened. The history of the particle is different depending on whether something looked. In 2019, a team led by physicist Massimiliano Proietti at Heriot-Watt University published experimental results in Science Advances that tested the Wigner's friend paradox, a thought experiment first formulated in the 1960s. Their results confirmed that two observers measuring the same quantum event can arrive at irreconcilable, mutually contradictory accounts of what occurred, with both accounts being internally consistent with the laws of quantum mechanics. Reality at the quantum level does not appear to be singular or observer-independent. It appears to depend on who is looking and from where. The most tested, most precisely confirmed, and most technologically productive theory in the history of science is built on a foundation that states physical reality does not fully exist prior to observation. Lasers, transistors, MRI machines, and nuclear reactors all operate on this foundation. It works with breathtaking accuracy, and after 100 years of confirmation, the question of what it actually means about the nature of reality remains not just unanswered, but so unresolved that some of the physicists who use it daily have concluded that asking the question may itself be a mistake. That unresolved question is not the deepest place where physics disappears, but it is the doorway to it. Number 1, the mathematical universe, the question physics cannot answer. In 1931, mathematician Kurt Gödel published two theorems that the mathematical community had desperately hoped were impossible. He proved that any formal system powerful enough to describe basic arithmetic must contain true statements that cannot be proven within that system, and further, that no such system can demonstrate its own consistency from the inside. The implications seemed, at first, to be confined to abstract mathematics. Then, physicists began to consider what those theorems meant for the laws of nature themselves. The answer was deeply, perhaps permanently, unsettling. Physics describes reality through mathematics. This is not a choice or a convenience. It is the only method that has ever worked at a fundamental level. In 1960, physicist Eugene Wigner published an essay titled "The Unreasonable Effectiveness of Mathematics," describing what he called a miracle. Mathematical structures invented by pure mathematicians with no physical application in mind, developed purely for aesthetic or logical reasons, have repeatedly turned out to describe physical reality with uncanny exactness. Complex numbers, non-Euclidean geometry, group theory, and differential manifolds were all developed as abstract mathematics long before physicists discovered they were the precise language needed to describe electromagnetism, general relativity, quantum mechanics, and the structure of elementary particles. No one has ever offered a satisfying explanation for why this is true. In 2007, physicist Max Tegmark at MIT formalized the deepest implication of this pattern into what he called the mathematical universe hypothesis. That physical reality does not merely follow mathematical rules, it is mathematical structure. The universe is not described by mathematics. It is mathematics instantiated. If Tegmark is correct, Gödel's incompleteness theorems apply directly and unavoidably to physics. There must exist true facts about the universe. Facts about what will happen, what has happened, what must be the case, that cannot be derived from any physical theory, no matter how complete, no matter how powerful, no matter how much data we accumulate. Not because we lack instruments, because the structure of logical systems forbids it. The universe also contains around 24 dimensionless physical constants, numbers like the ratio of the electron mass to the proton mass, the strength of the electromagnetic force, and the cosmological constant governing the expansion of space. These values are simply measured. No theory predicts them, explains why they take the values they do, or tells us what would happen if they were different. String theory, the most ambitious attempt ever made to unify all of physics into a single framework, does not resolve this problem. It deepens it, producing a landscape of approximately 10 to the power of 500 mathematically consistent universes, with no known principle for selecting the one we inhabit. The theory is, in the judgment of many physicists, permanently untestable. Every singularity in every black hole, every breakdown at the Planck scale, every contradiction in the firewall paradox, every quantum measurement that collapses a wave function without explanation, every physical constant that sits at its value for no derivable reason, all of these are symptoms of a single, unresolvable condition. We have built particle accelerators 17 miles in circumference. We have deployed space telescopes that can detect gravitational waves from collisions a billion light years away. We have measured physical constants to 40 decimal places, and every one of those achievements rests on a mathematical foundation that we did not design, did not choose, and cannot justify from inside the system we inhabit. The deepest place in the universe where the laws of physics disappear is not a black hole, not the instant of the Big Bang, not the interior of a neutron star. It is the interior of the only question that physics, by its own formal logic, can never answer. Why is there a law at all, and what decided what the laws would be? If you want to see more videos like this, click the video on screen now and make sure to subscribe.